Have you ever wondered how we take the incredibly abstract world of quantum information and turn it into something we can actually see and understand? It is a fascinating challenge to visualize a qubit state, which can be a complex superposition of 0 and 1. Fortunately, quantum mechanics offers us an elegant geometric solution for this very purpose. On the Bloch sphere, the vertical axis plays a special role, representing our computational basis states. To answer directly, the one basis state is definitively visualized as a point located at the very bottom, or south pole, of this three-dimensional sphere. It is a fixed and fundamental reference point for a qubit state. Now, why is it the south pole? The Bloch sphere provides a convenient way to representing the state of a single qubit as a point on its surface. The convention dictates that the zero basis state resides at the north pole, corresponding to the positive z-axis. Consequently, its orthogonal counterpart, the one basis state, must be positioned at the opposite end of that axis, which is the negative z-axis, or the south pole. This direct opposition visually emphasizes their distinct nature in the computational basis. Mathematically, any point on the Bloch sphere is defined by two angles, theta and phi, in spherical coordinates. For the one state, the polar angle theta is precisely 180 degrees, or pi radians. This value places the state exactly at the south pole, where the Bloch vector points directly downwards along the negative z-axis. Understanding this spatial mapping helps us interpret transformations and probabilities. Visualizing one at the south pole is incredibly useful for grasping how quantum operations affect a qubit. For instance, applying an X gate, often called a quantum NOT gate, physically flips the qubit state from the north pole to the south pole, and vice versa. It also helps us interpret measurements. If a qubit state is closer to the south pole, it means there is a higher probability of measuring it in the one state. An important insider detail about the Bloch sphere is that it only represents pure states of a single qubit, meaning the qubit is not entangled with another system and is in a definite quantum state. The radius of the sphere is always 1, signifying that the Bloch vector is a unit vector. This powerful visualization tool, though limited to single qubits, perfectly illustrates the continuum of possible superpositions and helps demystify abstract quantum concepts. Ultimately, understanding that the one basis state is mapped to the south pole of the Bloch sphere is a cornerstone for anyone learning quantum computing. This geometric representation allows us to intuitively see how different quantum operations rotate the state vector and how probabilities of measurement outcomes are visually encoded. It transforms abstract mathematics into a concrete, understandable picture, empowering you to navigate the quantum world with greater clarity.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.